Alright, this is a question about a cylinder, piston cylinder device. So a 50 litre piston cylinder contains nitrogen at negative 20 degrees and 1.7 bar. The cylinder is then compressed until the temperature reaches 15 degrees and a pressure of 4 bar. So during this process, 4 kilojoules of work was done on the nitrogen. How much heat was added or removed from the nitrogen? So they want us to find heat, whether it was removed or put in. So I'm going to draw a diagram to start with. Draw my piston. That's a piston in my mind, and it's got work in of 5. 5 work in, 5 kilojoules of work in. And perhaps it's got heat out. I'll draw it like that. Q, question mark, something like that. Now, we can write an energy balance, which is delta E of the system equals energy in minus energy out. So we can rewrite this as delta U, M delta U, the work in, and I'm just going to say plus or minus the Q because we don't know if it's out or in yet, but it should be out because we're compressing the piston, but I'll write it as that for now. Okay, so we have nitrogen, we have the work in, so we're going to need to find the mass, and it's an ideal gas, so we can use PV, that's volume, MRT. Okay, so we know that the pressure P1 is 1.7 bar. Now 1 bar equals 100 kilopascals. So 1.7 bar is 170 kilopascals. And we know that the T1, temperature at 1, is minus 20 degrees C. That'll have to be converted to Kelvin when we put it in this equation. It's compressed. Okay, what else do we need? R. So we can look up R in our data tables. And we can find that R for nitrogen equals 0.2968. And that's it. Oh, and V. Now we're told that this is a 50 litre piston. So if I divide 50 litres by 1,000, I get 0.05 cubic meters. So we know that the V, 0.05 cubic meters. Now, okay, we're solving for mass, so I'll write 170 multiplied by 0.05 over 0.2968 multiplied by, now let's convert this to Kelvin, so we must add 273 to minus 20, so 253. So our mass is 170 multiplied by 0.05 over 0.2968 multiplied by 253. So our mass is 0.1132 kilograms. Now how does this help? We can now use this equation to its full potential. So mass and delta U we know is CV delta T equals work in, and then there's plus or minus Q on the end. Now 0.1132 multiplied by CV, we can look up in the tables, is 0.743 multiplied by the temperature difference, which is negative 20 T2 minus T1, so 15 minus 20, which gives you 35. That equals, we'll substitute in the work, so 5, and then this plus or minus q term on the end. So we have 0.1132 multiplied by 0.743 times 35 is 2.9437 equals 5 plus or minus q. Now we subtract the 5 from both sides, so 2.9437. Okay, so we have this minus 2.0563. Now it equals, at this stage, we can now determine that it's q out of the system, because we can't have a minus q. So I can write, now I'm going to write q out. So then we just divide both sides by 1, or minus 1. And we get that, that's the q out of the system. Okay, so the second part of the question asked us to, so from 15 degrees and 4 bar, the piston is expanded adiabatically and reversibly until the pressure reaches 2 bar. How much boundary work in kilojoules is done in this process? Alright, so since it says it's a reversible process, that means that delta S, delta change in entropy, is 0. So we can use this formula. Delta S equals Cp ln natural log T2 over T1 minus R ln P2 over P1. Okay, now since this is 0, I'm going to add these terms to both sides, giving us R ln P2 on P1 equals Cp ln T2 on T1. Okay, now we can do that log rule where you put R at the top, or you put the term out front, to the top. So ln P2 P1 R equals ln T2 T1 Cp. Now the ln's can drop out and we're left with P2 P1 T2 T1 Cp. Now I'm going to multiply, so if we were taking the square root of both sides, we would do, both terms would be multiplied by 1 on 2, right? Or they would be to the power of 1 on 2. But since we've got R and Cp up the top, I'm going to multiply or put to the power both terms 1 on Cp, because we want to find the isentropic T2. Okay, so if I go P2 over P1 R over Cp, if I multiply that by T1, I get T2, or equal to T2. Alright, so we know T1 is the 15 degrees. So I'm going to put that to Kelvin. So 288 multiplied by P2. We're told P2 is 2 bar. So that's 200 kilopascals over 400, which is 4 bar, the original. And to the power of R, which is 0.2968 over Cp. So I'll have to look up Cp, and that is 1.039. And that equals T2. Now, well, just solve then. 288 multiplied by 200 over 400 to the power of 0.2968 over 1.039. And that equals 136.26 degrees Kelvin. Now since we have that, we have T2 now, we can go back to our original equation that we had up here, which said this one here. Okay, so since it's adiabatic, we can drop out the Q term, and we're trying to find the work. So if we come back down here, we can write M what is it? MCV delta T equals work boundary WB, where the mass is 0.1132 multiplied by CV, which is 0.743 multiplied by delta T, which is, well, what's our T1? 236.26 minus T1, which is 15 degrees. So whatever that was, 288. And equals the boundary work. Sorry, that was off the screen. There it is. Okay, now we're just going to put this in our calculator. That gives us minus 4.35 equals the boundary work. Now, considering it's minus, that means it's work out. And I think, oh yeah, it even says that, so it's expanded. So we could really just write this as, just drop the minus and say that it's 4.35 kilojoules work out.